I did this MSc. I started at Northampton 15 years ago, which is actually a hell of a long time now. And I'm going to make there's a few MSc students in the audience and a few past MSc students in the audience, and I'll make you smile a bit at times, especially the ones that probably feel aggrieved with some of the grades they've got from me over the years. Because the genesis of this paper actually goes back to a minor assignment on the Cosa Standards module that I attempted nearly 15 years ago. And I mean, we're all massively indebted to Philip Andrew for setting up the MSc course. And Phil, bless him, gave me a grade a couple of pegs below what I thought I deserved for this attempt. So I can see one or two wry smiles around the room now. So, you know, it's not the first time it happens when it happens to you. But Phil had asked set this assignment, and it's very similar to what is still CSM2. It asks us to look at the behaviour of a lift in response to the safety components, safety gear or buffer or whatever. And it's relatively easy to, you know, do a little bit of analysis using Newton's second law to have a go at this, especially with something with constant braking forces like a progressive safety gear. Incidentally, progressive safety gears don't have constant braking forces, but that was another story. That was the last time I stood up to do a presentation like this. That was 10 years ago. Once every 10 years I forget not to do this and get talked into doing it. So come back in 2023 maybe? So that was another story, progressive safety gears. So in looking to do a paper today, I went back to this sort of original formative experience from 15 years ago, and I looked at polyurethane buffers. And the reason this became topical, you'll hear from Ian Jones later that we've got new standards coming for EN 8120, but there was a discussion earlier in the year about stopping forces when a car hits a non-linear buffer. And there was a paper that I read to comment on, and I rather hoped it would answer a question in my mind: what sort of stopping rates do we have when a car hits a non-linear buffer? The problem is the paper didn't answer that question, and I still had this thing in my head that I wanted to find out more about it. So I actually did some work to figure out what the answer to that question was. And, you know, the next 20 minutes hopefully will unfold. Just to introduce nonlinear energy accumulation buffers, and you know, A&A have got some buffers you can look at later. They're these sort of rubber things that lift cars hit at the bottom of lift wells, especially if they're a low-speed lift. And you know, I've used them quite a bit in my career in the last 20 years, and certainly on low-speed, low-cost lifts, they've pretty much replaced the use of linear, you know, spring-type buffers in that time. So you know, it's a topical and quite interesting area. So a lot of lifts, you know, 1 meter per second or less. The Cosa Standards only comparatively recently actually fully described non-linear buffers. And the two crucial requirements they set for them, that first of all, the average stopping should be no greater than 1 G. But the other thing is that acceleration peaks, and there's a graph there of that's just taken out of EN 81. It says that the peak acceleration, where the acceleration is more than 2.5 G, that peak should be no greater than 40 milliseconds duration. But interestingly, it doesn't actually set a requirement for the level of peak acceleration. So in theory, you're allowed anything. And there is my question. What sort of levels would we expect with code-compliant buffers that we're using today? So to answer that, I need to do some analysis. And you know, you'll be very pleased to know that I've got about 7 or 8 slides full of maths coming up to go through and explain all this to you. But first of all, we have to model a buffer, a non-linear buffer. A linear buffer is dead easy to model because it behaves like a spring. its displacement is linear with its force. Non-linear buffers, by definition, are not so easy. So you can't easily write down a formula that tells you what the force is for a buffer for a given displacement. So I decided what I had to do is get hold of some data from various different manufacturers, and I actually got 18 buffer graphs which I digitized and curve fitted from 4 different manufacturers over a range of different heights, for a range of different speeds and for a range of different loads. But they all look relatively similar, and there was a question in my mind as how much these curves were comparable. There's a typical buffer curve. The blue line is what you get when you load up a buffer. You're measuring the force needed to displace it by a certain compression, if you like. And the grey or the grey line is what happens when you unload it. So it's not only is it non-linear, but it behaves differently as you unload it. Now that's quite interesting. The space between the two curves, it's essentially the hysteresis of the buffer. The energy the buffer will absorb is actually the integral of the force over the distance. So in other words, it's the area under the curve. So what that says is that if we hit the buffers, we get less energy out than we put in. In other words, the car will rebound slower than it hits the buffers. There's 3 main areas on the curve. The first bit's a fairly linear bit where it's small deflections, and then you've got a kind of plateau area. Looks quite useful. And really the bit we're really interested in is this bit here. Once you compress a buffer past about 65–70% of its height, the forces get very, very big indeed. Now I mentioned I wanted to model this, so it was a bit of maths, I'm afraid. So the first attempt was modeling it with a straight line graph, which I have to say has not come out there. Actually, none of these are coming out. Essentially what I'm trying to do here is find what is a good curve fit. And unfortunately, what you can't see on the screen, presumably because it's the wrong colour, is the polynomial that I'm trying to fit to the practical data. The good news is because you can't see it, I should go through it very quickly and cut to the chase, which is that the best fit that I found for that data was to find a 5th order polynomial. So in other words, an equation what looks like that. And that r squared equals 0.9997. R squared, when you do a curve fitting using Excel, it tells you this figure of r squared, which is a measure of how well the curves fit. And 9997 is extremely good. So what that means is I can take buffer curves and now fit a mathematical curve to it. So, which is great, because now I can take that back into an Excel spreadsheet or any other kind of thing like MATLAB, and I can do some work on it. And I did this for all 18 of these darn curves, and that takes some time because the data I had originally was not already digitized. And the buffers, as I already mentioned, were different diameters and different heights, and they had different forces, and they were rated for different working loads. But so I looked at them and I thought, well, how do I compare all these? And the answer was, I have to normalize them. So I actually rejigged my data to look at not compression in millimeters, but in terms of compression in terms of the percentage or proportion of the buffer height. So if I've got an 80 millimeter buffer and I compress it by 40 millimeters, that's now a compression of 0.5. And I normalized the forces by looking at essentially a force of 1 was a force to compress the buffer by 67%. So I then redid all my data, and I got that. What I actually found was that if you took loads of different buffers from different manufacturers for different loads, for different sizes, and you normalized the data, you actually had a lot of similarity with the characteristic curve that you get from them. And I have to say that if it weren't for experimental error and me having to do some of this work by hand, I suspect that that correlation would be much, much stronger. That means that we can actually take a buffer curve, a general buffer curve, fit a mathematical equation to it, and now we've taken it out the realm of a particular manufacturer's buffer, because they're all pretty much behaving the same, and we can do some general work on it. And that's good for me, because it means that, for instance, if I start sort of being rude about buffers, I don't get A&A coming after me because they've got some buffers on display and they think I might be slagging off their buffer. And I'm not, by the way. I'm sure their buffers are excellent. So what we're really saying is what we're talking about is generalities here. Here's the maths. So, good Lord. It's as comprehensible as that. So I do a little bit of analysis on a lift, and it's not hard stuff. And I haven't done things like take elasticity of the ropes or friction on the guides into account. This is a very straightforward, fairly, for me, quick and dirty sort of analysis. And if you know the sort of person I am, you know that quick and dirty is a very good description. And I had these questions on my mind that I wanted to address, and quick and dirty is good enough for me. What sort of accelerations would we expect if a fully loaded, free-falling lift car hits the buffers? That's one question. Second question is, what happens if it's in the same case, but with the suspension intact? You know, we're used to progressive safety gears. We're used to the idea that if you do a safety gear test with the ropes attached, and especially with no load in the car, that your stopping rates are higher than they would be for full load, and they're higher than if you actually had a free fall test. The third question is, what can we predict from that generalized curve that I came out with earlier? And finally, what are the implications for the new standard? Because the new standard has some new requirements in it. And the crucial one here is, you know, I put the curve up earlier and said the current EN81 doesn't limit the maximum peak acceleration. Well, the new EN8120 will do, and it'll limit it to 6G. And that will have implications. So I've asked 4 questions. This slide just blasts through the first 2. And essentially, and I've averaged. So I've got these 18 buffers I've looked at, and I've taken an average. But for a free fall case, using a load at the maximum specified load from the manufacturer for each buffer, I believe that we would see a peak acceleration in the range of 9 Gs, which is high. There's a range. I mean, the lowest was down below 4G. The highest was 12G. I've heard anecdotally that some buffers can result in stops of up towards 20 Gs. Now, even 9 Gs is very high. You know, we don't normally experience decelerations like that. If you're a fighter pilot and you were using an ejector seat, you know, you'd be looking at quite high numbers of Gs. Fighter pilots are young and fit, and they also accept a certain amount of risk in their jobs. But so the crucial thing here is that these deceleration rates don't exist for long. You know, these are less than 40 milliseconds. Now, the interesting thing for me is when I looked at running all this simulation with the oh god damn, I've used that S word, I apologise, I won't use it again. With the suspension intact, I ran all these pieces of work again, and I found something quite interesting for me was that the acceleration rates, peak acceleration rates, were actually lower, and actually were lower with lower loads in the car. And I wasn't expecting to find that, because that to me was counterintuitive. Just to remind ourselves of what a nonlinear buffer characteristic curve looks like. Now, going back to that general curve that I showed you, and thinking about free fall fully loaded case, which is what EN81 deals with. To do any more work on that, I needed to normalize again. So I've looked not at buffer heights or speeds. I've looked at a ratio between the gravity stopping distance from a given speed to the buffer height. That takes it out of the realm of, looking at individual buffers. I'm generalizing. And also I'm generalizing the force, the buffering force in relation to the load of the lift that's impacting it. And the reasons for that hopefully will become clear. And I'm looking at peak accelerations and average accelerations. Unfortunately, those curves are all coming up. This needs a little bit of explanation, so bear with me, please. For each curve is in relation to a different ratio between the gravity stopping distance and the buffer height. So in other words, to put something on that this blue curve at the top would be irrelevant if you were using an 80 millimeter high buffer to stop from 1 meter per second, which is something that we do quite a lot. Down at the bottom, this is the equivalent of using a 340 millimeter high buffer to stop from 1 meter per second. Okay, so it gives you a feel for the range of different heights of buffer or speeds relative to the height of buffer. And this figure here relates the, if you like, the rated load of the buffer to the load we're actually using. So if I'm at this end here, I'm using a heavy load compared with the rating of the buffer. And as I go towards this end, I'm essentially using a lighter load. So if I start from that area there, so this area here is really quite a high peak acceleration using a buffer, and it's happening because I'm using a relatively heavy load and I'm using a relatively short buffer. And immediately you can see that I can get down below this 6 Gs by reducing the load on my buffer if I'm on this curve, or I can come down here onto one of these lower curves, essentially by using a higher buffer or reducing my speed relative to the buffer. And that's pretty obvious, really. So if we've got a high stopping rate, what we're saying is that we either use a longer buffer or we reduce our load. But the interesting thing here is that, for me, is that these curves are quite steep in this area and quite flat in that area. So you can reduce load and it helps you a certain distance, but then no more. So essentially that says that the peak acceleration requirement in EN8120 when it comes of 6G will set the maximum rated load that we can use on a buffer, and it will set the, if you like, the smallest buffer height we can use at a certain speed. So in other words, the peak acceleration is setting one set of criteria, and the average is setting the other. So EN81 currently has a requirement for the average acceleration to be no greater than 1G. And again, these are different curves. There's my 1 meter per second for an 80 millimeter buffer. There's my 1 meter per second for a 340 millimeter buffer. And interestingly, as you take the load down relative to the rating of the buffer, the average accelerations are going up. Well, that means that meeting this 1G criteria in EN81 sets the minimum load you can use on a buffer. And that's why typically when you buy a buffer, you've got minimum and maximum loads. So I've got to conclusions quickly enough, and there wasn't too much maths, was there? The conclusions from all this are very simple for me. First of all, contrary to what I thought I might find, stopping rates with suspension intact are actually no greater than the free fall case. I guess to anybody that's been working on buffers over the last 20 years, especially the non-linear types, that's pretty obvious. And it means that when the guys who set the standards set the maximum rates, they can do it with a lot of security because they know that in practice people won't be subject to such high stopping rates. Part of the reason for that, or perhaps the main reason for that, is that as you reduce the load, the amount of energy that the buffer needs to absorb is reduced. And if you reduce the amount of energy in the buffer, because we're stopping on the very steep part of that curve, it means that the peak force is much reduced. EN8120, when it comes, will require peak accelerations of less than 6G, and on most of the buffers I looked at, the manufacturer will need to review their ratings, either on load, and in some cases it means that some buffer heights won't do the speeds that they believe they will. So there's a lot of re-rating coming. My hope is that the manufacturers of nonlinear buffers are picking up EN8120 or the draft of it and recognising that. But back on our side of the fence as lift designers, probably need to recognise that in the future we'll perhaps need a few more buffers than we did in the past. We'll need to reduce the load that we would have formerly placed onto a given buffer model. That's it from me. Thank you very much.
Thank you.